So, Michael Weber. He has a named professorship at UT Austin. He got his PhD from Stanford in mechanical engineering with a minor in EE. He has all the standard check marks for a very distinguished faculty, and you can read this in his official bio. There are a few things which I find really interesting and special. For one, he did a sabbatical here and wrote a book, which I think is nice. So he has prior exposure to Dartmouth. And second, when you look him up, you really fast go to a webpage of a movie from NPR distributed based on a book he wrote, which in my view is a signpost of a truly engaged scholar who knows how to communicate with real people, the decision makers. So it's not just some person in the ivory tower, but someone who can link the ivory tower to the people who vote and the people who are impacted by energy. And so I'm really looking forward to an engaged discussion. He has no slides, which is another second amazing way presentation. So without further ado, let's welcome him one more time.
All right, let's see if I can make this work. Looks like I have a leash now, so I don't know if you can hear me. I carry my own leash. I don't know if they can hear me online. Okay, hopefully that will work. It's nice to meet you. I'm Michael Weber, as you heard, professor at the University of Texas. And just a little bit more about my background to give you some perspectives. The key words that describe my life, and some of you who are at lunch heard this already, are energy and the environment and entrepreneurship and policy and engineering. So I'm an engineer, but I dabble in the world of policy and I also am active in the world of entrepreneurship. So I launched startups. I ran an incubator for about 10 years. And now I'm at a venture fund called Energy Impact Partners, which is a $2.5 billion clean tech venture fund as their chief technology officer, in addition to being a professor. So if any of you have clean tech startups, you need funding, you should come talk to me after this and we'll talk about that. So I'm really in the world of private markets and policy making, engineering, all on the topic of energy and the environment and how to make it better. And it's great to be here with you after a great sabbatical a decade ago. In the fall of 2012, I hid in a room in this next building upstairs outside of Karen Thurston's office, if some of you know her, and I'd close the door and hide every day and work on my book, which eventually was published a few years later, and then did another book that became this PBS series that you heard Klaus just mention. And as I'm trying to avoid PowerPoint in my life as much as possible. I think we all suffer from death by PowerPoint. So I thought I would just make some comments and then go into Q&A, so we talk about what you want to talk about, rather than just hearing me give a one-way lecture. But I do have some comments that might set the stage, and I'm hoping you will ask questions, and I will repeat the questions so that people on Zoom can hear that as well. But I want to give some sort of background on some of these keywords and why I care so much about energy. And some of it's just that if you think about it, energy is sort of like magic with what it does. I really am a fan of what it does for us individually and as a society. And there are a couple of ways I think about this with a cultural lens that gives me some perspective on why energy is useful or magical or capable for society. And there are a couple of myths that I use for this. One is, think about the myth of the unicorn. Now, from the entrepreneurial perspective, a unicorn is a billion-dollar tech startup, and that is not what I mean. What I mean is a unicorn that is a one-horned mythical animal. I think the mythology of the unicorn originated in the Indus River Valley of Pakistan. I'm not really sure about that. But this one-horned animal is very special. And today we think of it as special because it's so rare and hard to see one. We've never actually seen one. But really the power of the unicorn was that its horn could be used to treat water and make water safe to drink. It could rid a stream of water of poison. And today we've replaced the magic of the unicorn's horn with energy. We use energy to treat water to make it safe to drink. So that's kind of one way to think about it. Another example is the movie Fantasia. Have any of you seen the movie Fantasia, the Disney movie? Okay, all of you should go watch this movie. It actually holds up well. It's a Walt Disney animated classic from decades ago, from 80 or 90 years ago. And the idea that Walt Disney had was to put music to imagery so that when you heard music, you would see images, and also when you would see those images, you would hear music. So it's a classical sort of orchestration, this movie with a bunch of animations. And one of the classic scenes from Fantasia is Disney, the Mickey Mouse as the Sorcerer's Apprentice with the wizard's hat. So you've probably seen the wizard's hat, or you've seen Mickey dressed up as the Sorcerer's Apprentice. And the story of the Sorcerer's Apprentice is that Mickey is given the task, the apprentice is given the task by the wizard to go fetch water. You know, water is very heavy. You think of like a bucket of water is like 20 pounds. You have 2 buckets of water, it's like 40 pounds of water you have to lift. And usually the water is down low, so you have to get it from a well or somewhere, then carry it back up the steps to wherever you are. And this is a heavy task. And by the way, around the world, this task is almost always women and children who are given that task, this great burden. Imagine that with the daily life. And so he's given this chore, and it's too much work. And so Mickey thinks, well, I'll use magic instead. And so he uses a magic spell and gets a broom to go carry the water for him. And then the broom breaks, and then it multiplies, and then mayhem ensues. And then the wizard saves the day. But the point here is that Mickey was using magic to lift the water because it's so heavy. And today we use energy to lift the water for us with electric pumps. So we replace the magic of the unicorn's horn to treat the water. We use the magic of electricity to pump the water to elevate it for us. So this is a big part of the way we live every day. Let me give you another example from Greek mythology. There's a character named Tantalus. Tantalus misbehaved and was punished by the Greek gods, given eternal thirst and eternal hunger, and put in a pond of water below a fig tree. And as Tantalus would reach for the fig branch, the branch would bend out of reach, so he couldn't reach the figs. And as he bent forward to drink water, the water would recede out of reach. So he was always so close to water and so close to food, but could not quench his thirst or his hunger. And that's where we get the word tantalize, which means to have food or water just out of reach. And today we use energy and the magic of energy, the power of energy, to bring food and water within reach, to pipe it from thousands of miles away, or to grow the food, or to refrigerate it, or prepare the food. So you could say that energy gives us the magic to overcome the power of the Greek gods, maybe. So it's like not just magical, but it's like a deity, right? This is a powerful thing of energy, which I really like. And then one more example I'll give just for Klaus here is the medieval tales of Rumpelstiltskin. You probably know Rumpelstiltskin. How do you say it auf Deutsch again? Yeah, Rumpelstiltskin. So it's kind of the same. The same story, the medieval alchemist Rumpelstiltskin would turn things like hair or straw or lead, some worthless material, into gold. And he made a deal with the woman who was a prisoner that if she would give him his firstborn child, he would turn her hair or straw, whatever it was, into gold to make the king happy. And this is what the alchemy or magic of medieval alchemy was taking worthless, abundant materials and making them very valuable. And that is what the modern petrochemical complexes do every day. They take oil, and oil is worth less per pound than lead. A lot of people realize oil's worth like 50 cents a pound or something like that. It's worth less than lead. And they turn it into all sorts of pharmaceuticals or chemicals, or Chanel number 5, which at its highest version is worth more than gold in terms of dollar, like $10,000 per ounce for some of these Chanel number 5 perfumes. So that medieval alchemy of Rumpelstiltskin, whoever it is a daily occurrence, a continuous occurrence in the modern petrochemical refinery. So this is all the magic of energy. We use energy to replace magic. Why do you need magic if you have energy? And that's kind of just the imagination I imagine, like, wow, energy is kind of cool. And Arthur C. Clarke, who you might know as a science fiction writer, he published all sorts of great science fiction, but he had what were called Clarke's laws. And one of the laws was that any sufficiently advanced technology was essentially indistinguishable from magic. And so I like this idea of magic and energy and advanced technology all go hand in hand. So this is all just the allure of energy, is that it's kind of magical. But energy is also important. It's not just magical, it's actually central to society. So there's a man named Rick Smalley. Actually, some of you might know Rick Smalley, a professor at Rice University who won the Nobel Prize for the development of Buckminster fullerene, which is a buckyball, a carbon-60 geodesic dome structure of pure carbon that can be used for all sorts of new materials. And he died, unfortunately, around 2005 or so. And he spent the last few years of his life going around the world talking about the grand challenges of humanity, the 10 grand challenges. And he had this list. It's called Smalley's List now. And he talks about the 10 grand challenges, and he says, here they are. Energy, water, food, environment, poverty, terrorism and war, disease, education, democracy, and population. Those are the 10 challenges. And he put them in that order with a particular logic, with the idea that if you solve one, you can solve the next one. So if you solve our energy problem, if we can get access to abundant, reliable, clean, affordable energy, then we can have all our water problems solved because we can desalt the oceans, dig a deeper well, and pump the water up, move the water from thousands of miles, whatever it is. And once you solve your energy and water problems, you can solve your food problems because we use the water for irrigation and the energy for fertilizers or agrochemicals or pesticides or to reap the food. And then once we've solved our food problems, we can protect the environment, which is a precursor to lifting people out of poverty, which then you can use to avoid terrorism and war. And then you can turn your attention to tackling disease. And then education is a precursor to democracy, because for democracy to work, you need a well-educated people. Although I suggest to you we're testing that hypothesis right now as a world, so we'll see how that goes. And then you get to population. And population is on the list, but it's kind of last on the list. And this is important because a lot of environmental groups would say population should be first. We have a population problem. But actually, if you want to tackle population, the way you get there is with education, in particular of women, in particular of teenage women. And the way you get access to education is take care of these other problems first. You need energy to have a light bulb to read at night or to get to school because you need sanitation or whatever it is, and then you can get to population. So there's a logic to the 10 problems. And frankly, I agree that energy, water, and food should be the top three. And that's how I've designed my research program at the University of Texas. And a lot of my work is invested in these areas. At the venture fund, we invest in water and food and energy. So that's Smalley's list. So it's not just that energy is magical, it's actually very important to society. And the way it shows up in society is by its cross-cutting nature in every sector: the transportation, the lighting, the Zoom, the climate control on a nice crisp fall day in Hanover, New Hampshire. It is in our chemicals, our industry. It's in everything you care about. Energy, I mean, it's in the wood, right? So energy, bioenergy here, or the plastics made from petroleum or naphtha or something like that. So energy is cross-cutting. It's important. It's magical. Touches every part of society, and therefore we should care about it. So that's all just the context for why I care about energy and why I think you should care about energy. And I'm glad to see you here, because that's a sign that you're at least interested in energy a little bit. In the overall lesson, I would say, for energy, like if I teach you a semester-long class, the one takeaway I want you to have is that energy is all about trade-offs. That there's no solution that's perfectly bad or perfectly good. They all have good and bad. And the trade-offs are to get the form or the mix or the suite of options that maximize making us healthy, wealthy, and free, and minimize the ones that make us poor and sick and insecure. And we can do that. But even the worst ones you might think of, maybe coal or whatever, they have some real benefits that we need to keep in mind. And even the cleanest, best ones have some downsides. And those trade-offs are critical. So for us as engineers, scientists, analysts, thinkers, scholars, whoever we are, need to think about optimizing the mix to achieve the most of the good and the least of the bad. And that's the challenge from a market perspective, a policy perspective, or innovation engineering perspective, and a teaching perspective. So it's all about trade-offs. And because it touches every sector, it's like a bowl of spaghetti. You pull one piece of spaghetti, it touches the other. So it's not like you can just change one thing in isolation. It's all interconnected. So that's all me just doing rationalization for you and justifying why I do what I do. And I hope you buy it. At least I buy it. So that's kind of the story. And I hope you would think it's important as well. Now, that whole magical, cross-cutting, important context of energy is changing. And it's changing rapidly. We're in a phase of change. Now, energy always changes. We'll talk about that a little bit more. But it feels like there are decades where it changes more quickly. And we're in one of those phases where there's more change happening than before. A lot of you are too young, but the 90s felt like a pretty stable era or decade of energy was cheap. We had the wars, we had a lot of things. So we have episodes where energy is fairly stable, and we have episodes where energy changes a lot. And we're going through a lot of change right now. I think we're in a decade into a 3-decade phase of rapid change. I guess that's where we are. And we had that from the 40s to the 70s with electrification, and we had that in the late 1800s with second industrial revolution and then the first industrial revolution. So we have these episodes of change. And the change today, as far as I can tell, and there are smart people in the room who can correct me on this if I'm wrong, is a combination of 6 demographic trends and 3 technical trends and a 2-sided challenge. The 6 demographic trends are population growth and economic growth, industrialization, urbanization, electrification, and motorization. So we're changing demographically. There are more of us in the world, and we're getting richer. And because there are more of us and we're getting richer, and rich people consume more energy per person in general than a poor person, and there's more of us, is like compounded growth. So there's a lot of upside pressure on just demand. There's just a lot of demand for energy, food, water, soil, materials, goods, mass, all that. So that's one upward pressure on the system, is just the demographic change and upward demand. But because of industrialization, urbanization, we're changing where we use energy and how we use it. We're going from farm to factory, from rural area to city. So the location of energy consumption is different, and the purpose or end use is different. Instead of to make agricultural goods, it might be going to make factory manufactured goods. And because of electrification and motorization, we're changing how we use it from a personal or recreational perspective. We're using it for mobility and for freedom and for electrification of home. And electrification is really the desired outcome for the wealthy. Electricity is the fuel of choice for rich people. And motorization, mobility, is a desired outcome for rich people. If you are not rich, you use energy for heating and cooking. And as you get richer, you start to use energy to make yourself rich, and then eventually use it to get electricity and for mobility. And all of those are useful and valuable in the way we express our wealth in different ways of how we consume energy. But those 6 things together, between population growth, economic growth, urbanization, industrialization, electrification, and motorization, means everything's changing in energy simultaneously. We're changing what we use, where we use, why we use it, in addition to having more demand overall. This is a lot of stress on the system. And if we just look at the upward growth, we put some numbers on it. Around the world, a typical global citizen consumes energy. If the floor is 0, a typical citizen in the world consumes like 75 million BTU, which is up to my knees to say. A British person will consume like twice as much as the global average. So maybe a British person consumes 150 million BTU, up to my hips. An American consumes twice as much as a British person, which is up to my head. And a Texan we'll take one of you, maybe Klaus, on my shoulders to your head. Well, I mean, you might be too tall. Like texting consumes like 60% more energy than a typical American, and we like to pretend Texas isn't part of America sometimes. We'll say things like, if Texas were its own country, blah, blah, blah. So there's a lot of consumption, and for the billion people who don't have access, or for the rest of the world that wants to consume like the British or the Americans or the Texans, that compounded growth means something like taking today's energy system of 550 exajoules of consumption annually and multiplying that by like 10. I cannot imagine multiplying the energy sector by a factor of 10 without having extreme security, economic, or environmental impacts. And that's the challenge. Like, how do we solve that? So the whole system's changing because of those demographic trends, but then it has this additional context of technology trends. And there are three technology trends to my eye. One mega trend, overarching trend, is that of efficiency, increasing efficiency. We're using less energy to do things than we used to, and less mass. Light bulbs are more efficient, air conditioners are more efficient, cars are more efficient. We use less energy to give a lumen of light or a certain amount of heat or travel a certain weight, a certain distance in a car. And this efficiency is a good news story. It's a megatrend. Things just get more efficient with time as we get better at it, as we innovate and as we have technological learning. The second technical trend is increasing information intensity. So if the first trend is decreasing energy intensity, the second trend is increasing information intensity. We have more information, more data wrapped up in society and in energy. And actually, that's one of the reasons why we have greater efficiency, is because we have greater information intensity, more knowledge and data. It lets us run the system with greater fidelity and more precisely, and therefore we can use less. And there's some counter trends in as well. But the third trend is increasing decentralization. So the first one is efficiency. Second one is information intensity. The third is increasing decentralization or decreasing centralization. Instead of having large solutions far away, we'll have a smaller solution close by, which could be rooftop solar or microturbine or reciprocating engine diesel genset or whatever it is, or microgrid or battery storage for some of your off-grid stuff. And that increasing decentralization is a pretty important trend for the energy industry, because we spent 100 years plus centralizing for economies of scale, and now we're decentralizing for resilience or other reason. Now, we won't decentralize fully, but instead of decentralization being less than 1% of the solution, it'll be tens of percent of the solution. I don't know what it is, maybe 30-70 or 50-50 or something like that. And that increasing decentralization is showing up in energy. It's also showing up in water with remote water harvesting and remote water treatment. It's showing up in medicine, where instead of having a hospital far away, we'll have telemedicine and remote diagnoses a lot more, especially with COVID and especially with Zoom and the rise of these tools. It's happening with manufacturing, where instead of having a factory far away make a million of the same thing, we have desktop 3D printers making a million different custom things. It's happening with a lot of these industries, decentralization. Now, that changes the capital makeup, it changes the regulations, it changes who owns what, and these trends are important. Now, there's a counter trend in there, which is energy is becoming more decentralized or less centralized. I know that's kind of like a double negative or something. It's weird. But information is becoming more centralized. We used to have distributed information on your computer. Some of you have distributed information on your computer, but a lot of your data is at the cloud in a centralized facility. So as information becomes more centralized, energy becomes more decentralized. This is a counter trend. And as energy becomes more information intensive, information becomes more energy intensive. So there's some counter trends in there to be aware of for society that we're paying attention to. But those three technical trends are overlaid with the six demographic trends, which everything's changing, but then we have these technology solutions that are changing the solution set or the impacts or how we might think about them. And all of that is wrapped up in a two-sided challenge. And the two-sided challenge is, how do we increase energy access for the billion people who don't have it? They don't have access to electricity or modern fuels or piped water or sanitation, while decreasing the impacts for the 7 billion who do have it. And there's a lot of the environmental movement that's all about decreasing the impacts for those who have it, and maybe saying we need to use less. But without a doubt, there's a billion people in the world who should use more. And this is a great moral and ethical and philosophical imperative, I would suggest to you. And there's the energy industry say, well, we need to solve energy poverty, solve it for those billion, but they kind of maybe ignore the 7 billion people who have an impact that we need to reduce. And this is the challenge. How do you increase energy access, decrease the impacts while solving the 6 demographic trends and the 3 technical trends? And that's the setting for where we are, which is energy is magical, it's important, it's cross-cutting, it's all changing. By the way, there's some mega trends we got to deal with technologically, and then we have this pretty significant challenge of increasing access and decreasing impacts. And that, I think, defines a lot of the research space for me and a lot of people in this room. It defines a lot of the boundaries of the educational curriculum. What we need to learn and why is all wrapped up in those trends. And it should give you, I would say, hopefully a great imperative to think that your interests or work on energy are very important and impactful, that it will affect a lot of people. And it's central to the things you care about, finance and healthcare and freedom and democracy and quality of life, everything you might want. Now, the good news is transitions have happened before. We're in an energy transition. As I said, I think we're a decade into a 3-decade transition. We've done many transitions before. We substituted leaded gasoline for unleaded, and now we're adding in some biofuels. We substituted light bulbs at the technological level from incandescent to fluorescent to LED and that kind of thing. We used to have other kind of light bulbs. We had a different type of lighting. We had gas lighting and whale oil lighting and solid lighting with candles or torches. So we've gone from solid to liquid to gas to electric, and then within electric had some changes. So we've done these transitions on a technological level, and we've also had fuel transitions where in the United States, you back up a couple hundred years, and the dominant fuel for America was bioenergy, and then coal came along, and it became dominant from 1885 until 1950, at which time oil became the dominant fuel choice in America in 1950 through today, although this year or next, natural gas might overtake it. And then natural gas will be dominant for some number of decades, and then we'll go on to something else. The good news is gas is cleaner than oil, is cleaner than coal, is cleaner than bioenergy. Depends how you count the bioenergy intensity and whether you include life cycle or not. And so we're on a trend towards these lighter molecules that are less carbon intensive. This is good news. The fuels become higher performing, more efficient, and cleaner. However, the bad news is it takes a while. I mean, you heard me say from millennia to 1850 or 1885, then 1885 to 50, and then from 50 to 2022. So it takes decades. So if gas is the new leader, how long will gaseous fuels be dominant? Will it be 70 years? Will it be 30 years? How much time do we have? Probably just a couple decades, not centuries. So transitions happen before. This is good news. It usually takes us to a better place. The bad news, it takes a while. And technology transitions or substitutions have happened more quickly. I mentioned the leaded to unleaded and some of the light bulbs and that kind of thing. The question is, can we do it more quickly on purpose with policy and markets and innovation? That's kind of the question. How do we, the transitions happen anyway, but is there a way we can speed it up that's equitable and harmonious without being too disruptive? And the challenge I would say there for the engineers in the room is that the sad news is, well, the good news is we're innovative, we can do all sorts of things. Great. The sad news is the entire world economy runs on old technology. If you look at the primary energy conversions around the world, 60% of the world's energy conversions go through 4 devices: a gas turbine, a steam turbine, a gasoline engine, and a diesel engine, 60%. Now, I'm being polite to call those 4 devices. You could call them 2, right? Turbine and internal combustion engines. And that is where we get most of our energy conversions from. The rest are from burners and boilers and stovetops, burning stuff, which is even older technology than the turbines and internal combustion engines. Those devices, those 4 devices, were invented as recently as the 1890s. The gas turbine was like 1791, and the gasoline engine, the diesel engine, and the steam turbine were all the late 1800s. We're running the entire world economy on technology that's at least 130 years old. I think this is a disaster, and we could use some more innovation. So we should try some new stuff. We could try wind turbines, which were invented in the late 1800s, or solar panels, first demonstrated in the late 1800s. We could try batteries, first demonstrated in the early 1800s. Fuel cells, 1839. Fuel cells are pretty exciting. Fuel cells were written about in the 1800s by Jules Verne, French author, and then Gaston Leroux, who wrote Phantom of the Opera. I don't know if there are any Phantom of the Opera fans in here, but if you've ever read the book Phantom of the Opera, which is quite good, I recommend it, or seen the movie based on the musical, in the book, the French author Leroux talks about how the Paris Opera House used blends of methane with hydrogen to change the brightness of the stage lights. In the late 1800s, they were doing hydrogen-methane blends for brightness changes and for changing the stage effect. And today we talk about hydrogen blends of methane as like some sort of new solution. It's been around for well over 125 years. We could go power to fuels, where you use wind power to make fuels that you burn, just like the Dutch did in the 1700s. They would use windmills to crush oil seeds to get oil they would burn for heat and cooking and lighting. And this is kind of a disaster. I feel like, okay, there are no new ideas under the sun. Like, we need to step it up on the innovation side, because most of the things we talk about as a novel grand solution have been around for a couple hundred years, and we need to figure out how to make them cheaper or get implemented. So I urge you, innovators in the room, please innovate faster. We could use your innovations. There really aren't that many new technologies, and so we could use some brand new thinking. I was telling Professor Lee Lind earlier, I think that a lot of the innovations can be in the world of microbes and biology, mostly because I don't know anything about it. So I think that's where the magic will be next, and he can correct me if I'm wrong. But I feel like there's a lot of innovation to be had in different processes, different areas. All right, so that's the context. Energy is magic. It's important. It's cross-cutting. It's going through a lot of change. Change is great, but change is slow. We need some new innovations. That's why I hope you're going to solve the world. And I think this sets us up for what I believe to be kind of a logic for the solutions. And I often think about a 4-step solution sequence. or maybe a priority order is a better way to say it, or a taxonomy of solutions. And I think the first priority for solutions when it comes to energy problems is efficiency and conservation. If we can lower the height of the hurdle we have to clear, it's just an easier job for everybody. So we need to start with efficiency and conservation. This is the first and most important thing we can do. Now, that often is not investable. It's complicated for capital markets. It's not sexy policy, but it's actually very impactful. And these are the negatons or the negawatts. The ton you didn't emit or the watt you didn't consume is the most valuable. So we got to start with efficiency and conservation where we can. And that gets us partway there. It doesn't get us all the way there, but it gets us partway there. The second priority in my Michael Weber taxonomy of the four-step solution set is electrification. We need to electrify as much as we can. And electrification does a couple of things. One is the power sector is decarbonizing almost naturally. There's policy support, but it's just the cheaper solutions are cleaner these days. And so the power sector is decarbonizing. So as we electrify, we get the decarbonization from the power sector to whatever sector we're electrifying, heat or industry or transportation or agriculture, whatever it is. But also electrification builds with it certain efficiencies. This is especially true for light-duty vehicles. A gasoline engine is like 15 to 20% efficient. A diesel engine is like 20 to 25% efficient. An electric motor is like 90% efficient. And so you get much more efficiency. Even if you plug that electric motor into a 30% efficient power plant, it's still more efficient than a diesel engine. And so you get that second priority, that second priority of electrification helps that first priority of efficiency. As we electrify, we get inherent efficiencies. We see this with heat pumps. We see this in lots of places. Electrochemical separation is often easier, more efficient than thermal separation. So electrification is a way to solve the problem while enhancing that first step, which is efficiency. The third priority step is green fuels, because it's hard to electrify every corner of society. There are parts of society that are hard or difficult or expensive or nearly impossible to electrify, including certain types of industrial heat, aviation, marine shipping, maybe long-haul trucking. There are parts of society where it's easier, better to use molecules as opposed to electrons. Doesn't mean you can't use electrons, but it might cost more money, be less reliable, or take longer. And so there's a whole part of society that needs to be green fuels. Now, let's think about electricity. Today, electricity in the United States is like 40% of the primary energy goes to the power sector. In Europe, it's like 35%. In other countries, it's lower. If 40% of our energy consumption at the primary level is for the power sector today, we got to talk about maybe doubling that, maybe to 80%, 70, 90%. But plus, everything's growing, so it actually might be 2.5 times or 3 times. I don't think there are any people really arguing it's going to be 100% electric. There's probably 10 to 30% of the economy that will be based on molecules, not electrons, for a variety of reasons. In fact, some analysis from Europe that came out from DNV, a really trusted group, concluded that the cheapest way to get to net zero in Europe includes molecules for like a third of the energy consumption. A lot of that's for heating because of how expensive it is to heat in cold climates. And so I don't know what the number was, but it's, let's say 10% to a third. It needs to be molecules. Well, those should be cleaner molecules. Those molecules could be biomolecules. They could be traditional molecules that are cleaned up after the fact or at the point of emissions. It could be hydrogen or hydrogen carriers like ammonia or methanol or formic acid, or you can even use hydrogen to make methane. So it's some sort of green molecule. And I've got all sorts of bets about which ones it might be, but I think those molecules are really critical because there's some parts of society you can't electrify. And then the fourth step after you've done efficiency, electrification, and green molecules is carbon management. And the carbon management might be to make the molecules clean, but it could be at the point of the emissions or after the fact. Carbon removal, net emissions or negative emissions technologies are important because if you care about the speed with which we decarbonize or the equity and the equitable distribution of the jobs with how we decarbonize or the cost of decarbonization or the reliability of decarbonization, keeping molecules in the mix with carbon management will be cheaper, faster, more equitable, reliable than going 100% electrification, which will take longer and be more expensive, be more fragile. We can do some things to make electricity better, but that's kind of my view of it. And that becomes our investment priorities at the venture fund, by the way. Efficiency where you can invest, but boy, is that hard to invest. Electrification, green molecules, carbon management. That's it. That's the solution set in my view. And that is how I think we can deal with the two-sided challenge of increasing access and decreasing impact while accommodating the 6 demographic trends and the 3 technical trends. That's kind of my view of the world. Now, 2 last sort of postscripts on that before I stop, and I really want to hear your questions, is that there are a couple recent events that affect everything I just told you. The recent legislation out of Washington, D.C., which is really fascinating, and the Russian invasion of Ukraine has it been 7 months now? However many months ago it's been. And I get this question a lot from people. What does the Russian invasion of Ukraine mean for the energy transition? In my view, the Russian invasion of Ukraine is an accelerant for the transition. It will cause the transition to go faster. Now, it's a hiccup right now because coal looks like a very secure, reliable source of energy as opposed to Russian gas. So we're actually seeing an uptick in coal consumption in the world. But I think that's temporary. I think in the long term, it accelerates the transition because the secure solution is also the clean solution. And as the invasion happens, prices go high, the conventional options are not only insecure and dirty, but they're also more expensive than the other options. So overall, it's a hiccup in the transition for the next, 18 months, but I think overall it's accelerant, that the alternatives look cleaner and more reliable and more secure and domestic. This is true for Europe and the United States and elsewhere. So overall, I believe that the Ukrainian war, the Russian invasion of Ukraine, will move things faster. We're already seeing Germany saying we're going to keep nukes on a little longer, Belgium saying we're going to keep nukes on a little longer. There are a couple of people who are changing their policies based on the invasion. The second recent data point that's impactful is Washington, D.C. I mean, Washington, D.C. has been mostly dysfunctional and ineffective for years, I would say, for many years. All of a sudden, the United States has jumped from being a laggard to a leader. This is phenomenal, really, right? That we've gone from being someone who wouldn't take action on climate change to taking the most action. We're now doing more on a more aggressive timeline with more money and more comprehensive set of tools than the EU. And we wouldn't have said that a year ago. We wouldn't have said it 7 months ago. So this is a phenomenal thing for Washington, D.C. to go from part of the problem to part of the solution in such a quick turn. And it's not just the Inflation Reduction Act, although that's huge. It's also the Infrastructure and Jobs Act. So the Infrastructure and Jobs Act was a bipartisan bill with a bipartisan process. And the Inflation Reduction Act was a partisan bill with a partisan process. But they're both throwing a lot of money quickly at the problem with very clear directives, I would say, with 380 billion or whatever. That's a lot of money even for rich America to get things going quickly. And the way I think about this is with the Winston Churchill quote. He said, "You can always count on Americans to do the right thing, but only after they've exhausted every other possible option," right? This is a very classic American. It's very American to arrive late at the problem, throw a lot of money at it, and leapfrog everybody else. I think that's what's about to happen. If you look at just the announcements of battery manufacturers, California just announced and New York just announced today that they're going to ban fossil fuel light-duty vehicles starting in 2035. That's actually not that big a deal because GM and Ford and Volkswagen already said they're not going to sell you a combustion engine vehicle from 2035 and beyond. So there's a consolidation around the rapid timeframes. They're flirting with the idea of decarbonizing the power sector completely by 2035, which makes sense because most of the emitting assets will retire by 2035 anyway. So it's just a matter of what you build next. The amount of money I'm seeing in Texas, Louisiana going into green ammonia and green hydrogen and big facilities, it's just amazing. And so the United States is arriving late at the problem. We're throwing money at it. We're going to solve it pretty quickly, actually. I'm pretty optimistic around this. And that legislation really just accelerates the market trends that were already there. There are still disbelievers. There are still people who are holdouts. They will lose money. But there are some people who think climate change is a hoax, but like to make money and will build the things for which the policies support because that's where they can make money. And so I think between the Russian invasion of Ukraine and Washington, D.C. offering some federal legislation, everything I told you will probably move on a faster timeline. And I've emerged as a climate optimist. I actually wrote a piece I just published a couple of months ago about my climate optimism, because this is, I think, of all the things I've ever posted on Twitter. I've posted so many regrettable things on Twitter. There's so many things I posted I wish you would not read. But the thing that I posted that generated the strongest reaction, I've never seen a reaction quite like this, was I said, I'm a climate optimist. I think we're going to solve climate change faster than people think for less money, and it will be easier than we thought. And this generated all sorts of reaction about how crazy I am. And so I took my Twitter thread and turned it into an essay for Mechanical Engineering Magazine. Like, I think we're going to solve it. And we're going to solve it mostly because of people in the room like you. I think we're going to solve it because of students. And there are a couple of reasons I see that. One is students see this, in my observation, but let me know if I'm wrong, as their generational challenge. That this is your Cold War. This is your multi-decade challenge. And as you take positions of leadership and control, and people who are not on board retire or die, frankly, and you take positions, you'll take them much more seriously. I mean, I feel like you are a values-based generation that makes decisions based on what's good and not just what makes the most money. And that's different than my generation. And I hear someone snicker, so maybe you would just go for the money. You can, we can talk about that later. But I say when I was graduating as an undergraduate with my bachelor's in aerospace engineering, I would talk to my fellow students. I knew I was going to grad school, so I didn't have any jobs. So I would talk to them, what job offers do you have? Well, I've got job offer A that pays $42,000 a year, and job offer B that pays $44,000 a year. And those were prevailing wages in the sort of early 90s for an aerospace engineer. Which one are you going to take? Well, I'm going to take the one that pays $44,000 a year course. It didn't matter what the company was, that one was like saving kittens, the other one made nuclear weapons. That didn't matter. It was just about the money. But my observation of students today is that the values of the company will matter. That you're going to go work for a company you believe in. It's a values-based generation. The investors are demanding it. The investors are putting pressure on the companies to say, you got to clean up your act or we're not going to invest in you. The employees are demanding it. So if you want to recruit or retain employees as a company, you have to clean up your act. And the consumers are demanding it. So if the investors, consumers, employees, and everyone else are saying now the policies, you have to clean up your act, we're going to clean up our, I mean, I think it just happens that way. When everything aligns, it goes very quickly. When the markets and cultural forces are, and the policies are all pointed the same direction, things move quickly. And quickly, I mean like in a decade. Think of the shale revolution. We went from net importers of gas to net exporters in less than a decade because markets and policies align around the need to produce more natural gas in the United States, and the technologies are finally available. So we went from declining gas production to now increasing. We're setting records every day now on gas production in the United States, which is really phenomenal. And that turned on a dime being a decade, it turned quickly. So I think massive complex systems can move quickly if everything's aligned. And I think all these external national security events, which mean we have a coincidence of an energy crisis, a security crisis, and a climate crisis all at the same time, is just fuel in the fire, so to speak, to accelerate this. And then you combine with your attitudes of what you do will make it really get to the right solution. So I'll stop there. I appreciate your polite attention for me just rambling on for all this time. I think we still have like 20 minutes left. And what I'd love to do is if you have any questions or comments or corrections or insults, if you could offer them, and then I'll repeat the questions for our guests on Zoom. But thank you very much for having me. It's really a pleasure to be here.